Or good evening, everyone. Welcome to our Sunday event with Dr. Tax. And Dr. Tax, can you introduce yourself and then introduce your topic? It's all yours.
Thank you, Professor Ma, Dr. Ma. This is Dr. Kunal Das, working as a assistant professor and senior grade in computer science, Department of Computer Science, College.
Dr. Das, your audio is not coming over.
I'm audible. Actually, my voice is some problem. Am I audible? It's okay?
Yes.
Okay. Just taking about that. My today's topic is a PSO inspired global neighborhood based qubit mapping, a new approach. Very recently, we have published this work. And so many persons are waiting in a waiting room by making.
Let's begin. Yes.
Now, the question is, main issue is that if we have our computer program, what we have written in a quantum computer, which are basically in a logical based quantum computing, what we have done in a logical program. Okay. In a logical programs and actual physical qubits are different two realities. So some graphics can be definitely realized that our logical qubits are actually need to being mapped in a quantum or physical qubits in an actual chip diagram. And in this process, we definitely required to map the logical mapping, and then is required to find out the qubits what we are actually going to map. They require a number of swaps, and these swaps operations need to be optimized in the process of qubit mapping and qubit optimizations. What I actually want to say, let us see one figure. This. So this actually arbitrarily we code it. For example, if I code it like this way. Suppose I plan to make Q0 with Q1. So Q0 and Q1 is actually in a direction of this. I want these two pair should be connected. But unfortunately, suppose in a qubit, there is no Q0 and Q1 is connected. Let us write in a capital Q0, capital Q. And there's a Q2. So these two are connected, but these are also connected, but Q0 to Q1 has no connection. But we want in a logical program, we have given that Q0 and Q1. So what to do? If this program goes to in a physical qubit physical device, then this will create a embedding problem, because Q0 and Q1 no longer exist a connectivity. So what we can do, that in a logical to physical, we can map the Q0 in the sense of Q2 and Q1 in a sense of capital Q1. So that means we are going to map, that's called initial mapping, with Q0 as in a logical domain or virtual, logical or virtual, and is a physical is Q2. it was Q1. It was the Q0. And Q1 is physically mapped with Q. So this is the problem actually remain in our question, that how we actually map this logical program into a physical one. This is the problem. So in this problem, what are the different flows, importance, that how we make a, it's the initial case that I shown that if I mapped correctly in a small case I have explained, then no doubt about the question of swap count. But in a complex circuits, I will show again. In a complex circuit, you need to record the number of swap count. Why the swap count is important here? Suppose one logical qubit you want to map in some physical qubit, and this physical qubit may not have directly connected, but it is closer. It is closer connectivity. It is closer connectivity to all others. Okay. So then that closer connectivity required the number of swap count to select appropriate logical qubits. Now let us move to the next slide. The two world actually, logical qubit circuit and physical quantum device. This is the on-paper design of quantum algorithm, what you have want to code, and after coding, you have generated a program which actually qubit are considered, which are no longer related with the physical qubits. You have coded as you want to. So that's why we sometimes say these are virtual or logical qubits. And in that case, what happened? Programmer designs these circuits that do not match with the physical operations in the algorithm. But in a physical qubit, these are actually quantum actual qubits which are available in a quantum chip. Qubit have a fixed positions and limited connections. What affect in a limited connections? It is the connectivity that is predefined. Oh my God. We continue. Let's move to the target. Now, what over there? The actual qubit in a chip. Now the qubits have a fixed positions and a limited connectivities. Okay. So once this qubits are fixed positions, then what happen? They are not able to move. That is, you need to propagate your information from one qubit to another qubit, right? Because suppose you require the, now the qubit has a fixed position. So what are we talking about? Logical qubits are not talking about. We are talking about the physical qubits, and physical qubits and connectivity. These are the fixed. Now the few qubits are we have logically physically considered, but they may not have a directly connected, because in large circuit we found that some two qubits are not logical physically connected. Then we need to swap the information from one qubit to another qubit, which we have selected as our desired qubit to map the particular logical qubits. Okay, so that is the adjustment, or that we have made a connective qubit for physical qubits with a logical one. So the problem is what? There is a mismatch between the ideal circuit and real hardware constants. So that's why the this translation for the ideal to real is called a qubit mapping. Okay. Now let us let us go for the what is the why qubit mapping is required, or why this embedding is required. Because of connectivity constants, we have given a one problem. We make a code which is actually uh, ideal uh, qubit mapping we have considered, but it's no longer connected with your physical qubits. And second thing is that why cannot we cannot make a embedding over directly to physical? Because which device, which NISQ device we are using, or we will be using, this code will be using, we don't know. So in this way, two things is very important. As you know, the program which you have written in a source code need to be compiled. Similarly, here transpiler is important, because this transpiler will create a translator circuits. This transpiler is the concept of getting the qubit mapping. And why it's required? I have says that because the in a logical program, which is the constant for every time, but in a physical, the your quantum hardware or quantum chip might be changed. So we cannot make a fixed mapping uh, hardware program. So that's why we required, according to our hardware, we will create a transpiler, and according to transpiler, it will generate a physical program code, which will actually making a embedding with a hardware or quantum chip. So these are the all consequences might be happen, and solution is the mapping process might find the way that interacting is possible. Now, code solutions with using the swap gates. Swap gates, what swap gates can do? Swap gates are exchanged the state of two adjacent physical qubits. So if I required one, suppose initially in initial mapping I consider a one physical qubit, but final mapping I considered another qubit is a physical qubit. Then how many swap I required to reach the final qubit? That is the swap count we can count. Okay. So now the problem is that the swap count and swapping is also not a free, because it has some cost, and that cost means the requirement amount of time. So the main goal become minimum number of swap counts or swap gates usage. If I able to optimize this problem, then definitely this problem or a translator circuit will be optimized to get into your logical to physical mapping. Now, the two phase we can consider for this problem of qubit mapping. One phase is initial mapping or initial placement. What we are doing actually in initial mapping, what we do in our first assignments, whatever the logical qubits we have, we just consider a simple one physical qubits, that which actually maybe the significantly reduced the swap count. That gate will be required later on, definitely. And the strategies is often involved to analyze the interactions in a logical to place the frequently interacting qubits close to each others in a physical chip. Then the second step required the qubit routing. So first we have chosen one qubit, logical qubit, which has more connectivity just for placement purpose, which has a more connectivity. That means if I consider logical qubit mapping as a graph, so then we get the degree. So each and every node are considered as a qubit, and each and every qubit now has degree. Which qubit has a highest degree? We have a possibly highest choice, the selecting for an initial mapping of that qubit. Now, since I considered the highest degree, so in a qubit routing, in this dynamic process, the swap counts or swap gates to resolve the connectivity with the non-adjacent qubits. Compiler must decide which swap to insert and where to place it, and as well as place them to minimize the overhead. Okay, so that means we have so many uh, list of what I say. This is node or qubit has a degree, the same degree connectivity. So now on the pool of same connectivity, we have selected one qubit for the placement. If we have selected one qubit as a placement, now the next phase is coming, that the qubit routing. So qubit routing is required because then the non-adjacent qubit, how they can connect. So among the list, which one is the least, that is will give you the number of swap count lesser and lesser overhead for the different swap gate usage in a transmitter circuit. Now that how the strategies can be implemented, first is the placement and second one. This is the common approach which are followed. Some heuristic approach, heuristic sub approach are reported in early one. Look ahead strategies also given. This is the one example, that ASABRE. This algorithm we have compared with our work, and some algorithms are there, divide and conquer, and some they are considering the hardware fidelity to make a qubit mapping. And obviously minded, the qubit mapping is a complex optimization problem. It's a NP complete problem, and various heuristic algorithms are used. Some heuristic algorithms are fine, very well, and some found not so good for that cases. Now the challenges, definitely navigating the complexities. So we are navigating this because as long as the scalability increases, so optimal mapping become actually the exponential harder problem. So as the number of qubits and gates increases, if we go for 1,000 qubits quantum programs or quantum computers, so definitely it will be making us burden for us for logical to physical mapping. And that's why this is a very open and very important part of computing, other than the one algorithm we have developed, definitely. The second part is a translator. So the transpiler you need to give, and then after this, then the transpile circuits you require. Then definitely the question about the noise and errors, because if every addition of swap gets introduced, and probability of more errors. So reducing the number is a one important part also, because if my translator is so bigger, after the transpiler we have generated the one transpiler code or transpiler circuits, and that become big enough, and then you are introducing or inviting the error and noise. And the gate execution time, definitely if you don't have a good mapping, which is not optimized or minimize the number of gates, then the total execution time of circuit also increases. So these are the challenges we need to overcome uh, once we are going for considering the 1,000 qubits quantum computer. So in a IBM, what IBM has done in a IBM Qiskit, the transpiler passes the following stages. So first they have an init process. That the init is a fast process. They have considered, and then second one is a layout process part. That is the layout stage. The layout stage is basically initial stage. Okay. So after that we have said that routing, and then they have given a translation. They have applied optimization process, and then finally they make a scheduling. So this process known as a transpilation process, or we can say this is a transpiler or transpiler, like a compiler. Now let us move to this program, which I have actually shown. It is actually layout stage. Here you can see the Q0, Q1, Q2, Q3, Q4, and the late. These all are logical. Okay. So this is a 5-qubit program. In a 5-qubit program, first you have applied Hadamard, then C0. Fine. Then C0. Fine. Now after that you have a barrier, then you make a measurement. Fine. So all are classical registers which are measuring. So this is your virtual or logical code or logical circuits. But what actually we need to do now? How we make an initial placement? How we make an initial placement with the value of Q0, where Q0 will be initially placed over which device? So device is important. Which quantum device you are going to make your backend? So if your backend is like this device uh, graph, mapping of each and every qubits are like this graph, then you probably getting that the 0 and 4, these two are same degree. Their degree is 2, and 12 is the degree is a 3. So you might have a chance to map to 12 if go for our procedures. But they have considered the first initial placement. The initial placement they have made as a qubit Q0. Fine. And then Q1 as a Q1, Q2 as a Q5, Q3 as a Q6, and Q4 as a Q7. So this is the IBM strategy. I'm not giving my strategy. Once I discuss my strategy, you probably get my strategy first place, that this Q0 is the 12, because we have considered degree as our first initial placement strategy. Okay. Now let us move to next gap. Actually, what we have considered in our problem, and this dynamic remapping to logical to physical qubits in transpiler enable the 2 qubits gate algorithms. Actually, we have seen that all problems which are discussed in a basis of 2 qubits gates. Previous solutions which we have found that much remapping suffers the high complexity and poor mapping quality and limited flexibility and controllability. Nearest neighboring optimization of a quantum circuit, as we have proposed, is not explicitly applied in a 1D, 2D layouts, and assumed it work which have been sufficiently less restrictions. And there is some heuristic methods also. There is the fast local search-based heuristic method that also have some limitations, and that limitations we will found in our comparative studies. Now we have gone through with our 106 qubit physical device which are available in IBM, and we try to map all 2 qubit gates. That is the total limitation of entire research or the mapping. Everyone doing 2 qubit mapping and very fundamental circuits we have considered, that is C0. Now these are the first initial placement, and why these are initial placed took place, we need to go with study with this point of view. So let us move to that. The logical qubits to physical qubit mapping, what we have used, that PSO inspired global neighboring qubit mapping. Here we have introduced a particle swarm optimization to optimize the routing, as it is optimizing the routing steps, and initial placement we have did with the degree. So in together we get the highest reduction in swap count, and in that case the fitness value or fitness function we have defined, and this fitness function is based on your degree. Okay. Now let us see the system model of fitness function. This you can see the fitness function is defined as sum of swap count. Definitely, if you have initial fitment or initial placement you have done, now you have the circuit which you can consider the sum of the swap counts what is required to module and degree difference. So if we consider the sum of all degree difference with each particle, okay, so particle is what? Here particle is entire mapping. So each and every qubits has a different mapping. So in respect to that, the placement of each qubit, you have a single one map. Up to that, you have a n number of maps. For a there is a n particle. So in n particles, we have now considered the one thing, that swap count plus degree difference. That is, in a degree of logical qubit minus degree of physical qubit. And this sum up. After this sum up, and this is considered as a modulo operation. That means we are taking only the positive values. So after this sum up, you get the f value. So which case the f is reduced, then that will be the optimal mapping you have resulted. Now let us consider this logical circuit. You have a Q0, Q1, Q2, Q3, Q4. Now you found that Q0, Q1, Q3, Q4 with a degree, some are 2 and some are 3. So once you have a degree 3, for example, Q2, if I am talking about the logical circuit only. So how you come to know that the Q3 is a degree 3? Definitely, you can say that Q1, Q2 is working with the Q1, Q2 is working with the Q3, and Q2 working with the Q0. Okay, so then the logical qubit Q2 has 3 degree, right? Because it is working with the Q1, it is working with the Q3, it is working with the Q0. So it is a Q0, Q1, Q3. So Q2 and Q3 now need to be placed where? In the physical, right? So this is the logical qubits with degree and neighborhoods. Now this is your physical part. This physical part I try to put into a 1 qubit, which is the initial mapping, which has a maximum, or it can make a summation 0 or a less. If it is such that we need to find out that the degree of Q2 will be placed with at least equal to same degree in a physical or higher, then it will be less. But if I have a exactly equal 3 qubit 3 degree, because Q2 has 3 degree 3, so if I have degree 3, so then the summation part of fitness function is reduced to 0. Okay, and lower value of f will be the optimized circuit. Now Q2, so Q2 initial mapping in a gate Q2 to Q1. Here is a Q2 to Q1, first one, Q2 to Q1, this one. Now in a mapping, I want to make it initial mapping placed that Q2 with the degree is a 3, and Q4, here is the Q4 in a physical qubit, which degree is 3. So then I choose the Q2 is directly made into Q4, and in that case the fitness value is 0. Why fitness value 0? Because I mapped this into physical as a initial mapping. Fine. And the fitness value 0 because the summation of their degree difference is a 0 in all possible cases. Now Q3 to Q4, let us see the Q3. Q3 also similarly, the degree is the 3. So Q3 also degree 3, as it is connected with the 4, as it's working with the Q1, as it is working with the Q2. So Q1, Q2, Q4. So this also 3. So I need to choose a one qubit for that, and that I choose because Q3 and Q4, because the Q3 are Q4 are same in a logical. So I consider that Q3 is a Q4 and Q4 is mapped with Q15 and Q4 is Q15. So then again their difference of degree is 0 and the swap count is also 0. No operation needed. Now move to Q1, Q3. Now move to Q1, Q3. That is the Q1, Q3, this one. And what is the Q1 and Q3 degree? Then Q1 can be placed either 15 and or Q1 can be placed 23. Let's look at that in details, that how we choose after placement the routing took place in that case. Let's see. So this is the case. You can see the Q1, Q3. Q1 is mapped to Q23. Either it is a 2-3 or in the 15. We have considered two cases. Okay. Now two cases are shown here. This is the first Q3. Yes. Q1, Q3. So Q1, Q3 mapping. These are the previous one. Q1, Q3, it is the mapping. So now I find the degree of QI, that is the QI means Q1, Q3, and degree of difference of Q, degree of QJ, and plus swap count. So mapping of this position 1, that is your routing actually took place. 1 is mapped to the 115. If Q1 mapped to Q15, then what happened? Then FA, cumulative sum of degree difference of two mapping and swap is considered. Now, where is the Q1? This is the Q1 and it's moving towards Q2. So you can see the Q1 will first move to here. So that means you required one swap first. Okay. And then I required to mapping 1 and then mapping 2. Q1 is moving to Q4 and Q4 is moving to Q1. So then I reach Q15. Okay. So if I choose a Q15 from initial mapping with a 5, then I required this amount of movement. Okay. So this amount of movement required 6. Total is a 6 because fitness or degree count is a 4 and plus 2 number of swap you required. 2 number of swap you required. Okay. So one swap is required Q0 to Q1 to move at position 4, that is physical qubit 4, and again physical qubit 4 to physical qubit 1 you move. So upper the small letter is showing that logical qubit moving. So this direction to this direction is move, you required 2 number of swaps to hopping. Okay, so mapping 1 and mapping 2 shows that what is the fitness value you get. This is the 6 with the number of swap required 2. Now if I move with the first choice, this will be 2 swaps. Okay, and definitely one Hadamard gate will be required. Then the fitness value is the 6. But if I go for choice number 2, that is Q1 to 23, what happened? Then let's see the Q1 to 23. So Q1 to 23, that you required number of swap, what? You moving Q1 to 23. You can move that way or you can move that way. So in that way, you require 1 swap, 2 swap, 3 swap. So after 3 swap, you will be in a 23. Okay, or you might be moving this way. Okay, so total fitness, whatever you count, if you count this way or if you count this way counting, if you done, you get 8 number of swapping. As I started that this way is a 8 number of swapping, and this way is a 4 number of swapping. 1, 2, 3, and 4. 4 number of swapping. So this total, is it possible or not? This is another question, because if it is directed only to these directions, then this is the only way. I think in a study we have found that this is only these directions, because this is the directed graph. So connectivity is the direction is given. So that's why this direction is considered in this computing, and in the result you get the fitness value is a 8 plus 3. 3 is the degree difference, and 11 is the 8 is the your number of swap. So it's a 11. So definitely out of 11 and 6 is a optimized value is a 6. So we will consider the first choice of 1 to 15. So I will map logical qubit Q1 into 15, not in a different other cases. So Q1 will be mapped to Q15, right? So I explained this everything. And next again, the Q1 to Q3, that how the Q1 and Q3 will be mapped. So that also explained here. So you can see that the mapping 1, that the 2 mapping I've shown, in a mapping 1, if I map to 15, then it required a 2 number of swaps. Okay, so I want to make a mapping a Q1 into Q2 in a 4. In a 4 I have mapped, and if I go for another steps, that is the 15, then I required 2 number of swaps. So it is easy to understand that if you choose the only the Q4 with a less number of swap required, where you consider the Q15, the swap count is high. So this way you can provide the appropriate your logical to physical qubits mapping for entire circuit. And now the question is how the PSO help you do that, because PSO will continuously calculating the fitness value, and fitness value ultimately gave you the appropriate correct routing, and in the correct routing you are reducing the optimized cost optimization, and number of swap optimization you have done in a routing phase, and your initial mapping we have considered on a degree of each connected or connected qubits, logical physical qubits. So now let's move to the algorithm for understanding. The first algorithm is how the count the number of swap requests in a problem. If you have a number of counts, then that will be used for calculating the your fitness value. So total swap is initialized to 0, and you have a pair of mapping from Q1 to Qi and Qj. That is for initial mapping. And if initial mapping is directly connected, then is the continued, no problem. And now need to find out the shortest path between Qi and Qj. If the Qi and Qj are appropriately mapped for I and j or not. So I and j are mapped. Initialized map is correct or not? Because if might require a routing, and in this routing phase, which of the number of swap is required, that is our intention to count swap function. So just simply that the length you have calculated and the number of swap requires you have applied. So as in the previous example we have shown how the swap operation took place to older physical qubits to newer physical qubits. So that will actually finally return you the number of swap count. Now, where the swap count will be used? Where the swap count will be used in a counting the fitness value. So now let us go for the next algorithm that is the second algorithm in our problem, that is PSO for qubit mapping, which actually return the actual optimal mapping considering your fitness values. So what is actually you use we have taken a solution GNB algorithm randomly initialized the populations. So initialize done and assign random velocity to each particle. So as I told you, the every graph for every qubit are called as a particle. Now for each particle you have counted the swap count. The swap count is a number of requirements for one physical qubits to old physical qubits to new physical qubits. So these swap counts are counted by count swap function, and now the calculate the previous fitness value, that is initial fitness value, we can say the swap count and summation for the all particles. You have get the degree difference. Now the p best you have initialized the initial mapping is coming to the p best, and g best is the global initial fitness value. Mapping with lowest fitness value will be the g best. So we are considering that fitness value which is the minimum, that is the lowest value, will be the winning choice of optimal mapping. So that we initialized as a ij as a g best. Okay, so each and every swap particle swap optimizations, their velocity and movement with considered as a function of p based and g based, and you calculate the velocity and distance of separations. So then you count the swap count from the swap count. Again you refresh the swap count for the new fitness value calculation. And for the new fitness value calculation, if the swap count and summation of degree difference between logical and physical, if the fitness value is the lesser than the physical previous fitness value, then definitely we need to change the current swap value and the p based and g based mapping. So g based is now the mapping with the lowest fitness value will come. If the previous fitness value was higher than the current fitness value, if the current fitness value is lesser, so that will be the g based. So finally, after completing the entire choice of fitting, that g based will return, which g based is actually your optimal mapping for the given problem you get. Okay, so after running this over the PSO parameters and GA based parameters, you can see the number of particles as 40 iterations we have done 1000 times, and parameterized and social parameter given, and GA parameters, the population is the 40, and generations and mutations all are as crossover is given this way. Same considered we have. Now the after these two, if we see that the crossover rate and fitness values with the with the crossover and mutations, what result we have get from that, and fitness across the PSO parameters, you can see the variation of fitness with the varying the PSO parameters. This is the PSO parameters are varying, and crossover rate we have considered. Now comparative analysis, you have if you go for the GA is a optimization process, and then PSO, that these two evolutionary algorithm showing that one is this one is a GA where PSO is more effective. Okay, so these are the execution time in terms of calculations. So PSO is a standard deviation is high, but convergence is faster, and execution time is also lesser in terms of GA. So now the PSO and GA on the benchmark circuits we have applied. So the result is now applied over benchmark circuits, and in this benchmark circuits you can see the number of qubits. We have considered that what is the number of qubits are there in this benchmark circuits which are there. These all are the using model 10, mini ALU, all these are available in as a benchmark circuit. You can go for experiment for this for proposal, you can go for that, and these circuits are concentrated up to 10 to maximum 16 qubits, and you can see the number of operations inside this is a 173. So 173 2 qubit operations are there, and the circuit depth if you go, that is highest is a 1644, and now the execution time what required for your proposed that is our PSO based mapping, that is relatively lesser with a GS. You can see that highest depth, that is actually some 25.4 nanosecond milliseconds, where is the 6.117. And now the average number of operations also a little bit nearer, but it's lesser. You can see that this also lesser in case of average number of operations which we have required for this purpose. Because if you get the transpiler circuits, though, so after transpiler you get the transpiler circuit, and this transpiler circuit has to be larger than your actual number of operations. So how this are actually you able to optimize, that is important. So GA actually optimized in by 238 operations. That means you have used Adawad as well as Swapgate. So in our case it is a 226. Okay, so average depth also reduced. You can see that 172 is a average depth of GA, where the average depth is 154. So so every transpiler circuits are reducing in our proposed model, and highest depth similarly you can see little bit better compared to GA. Now we have compared very interestingly the proposed model with IBM approach as well. So transpiler used in IBM, which are reported here, we can see the execution time, average number of operations, average depth are really lesser in compared to PSO based mapping. Okay, so you can see that same benchmark circuits we have used, mini ALU, then the 10 number of qubits required, 173 number of operations, depth is 69, where you can see the IBM required execution time in seconds, 10 seconds, where it's a 1 second, 1.015 seconds. And interestingly, the number of operations are required in IBM, it's around 176. Okay. And in our case, the average number of operations is 2 to 6. And one thing very important, the depth also reduced. You can see 303 is the depth for IBM, where the average depth is 154 in our case. And you can compare with the previous method, that is already we have given the genetic GA algorithm based. But now next is this one. We also compared with the best found your today. Currently, before the PSO method comes, this was the best proposed model apart from IBM also. So we have compared with this problem also with some benchmark circuits there, which are given in a 16 also as well. So we work with that also, and in that case we found that the number of circuit in the original circuit is the 10,000 number of gates in the original circuit is the 10,223. Okay. Now in a average gate mapping or number of gates required is a 14,567, while in our case it is 11,315. So every cases there are win-win situation in our way. Okay, so this is all about our proposed problem. If you have any question, and this reference also given, if you have any question, I'll be happy to answer your questions, or if you have any idea or thought, you can contact me for collaboration. I'll be happy to share many problems in that transpiler designs. We are planning to make a proposal on a transpiler in our DST as a National Quantum Mission proposal. In India, we are running by a Department of Science and Technology. One certain mission is there, that a mission 2030, which is actually National Quantum Mission. And in that, we will develop indigenous 8-bit qubit quantum computer, 8-qubit quantum computer. And for 8-qubit quantum computers, the software part, the metawire, this is the metawire actually. And this metawire is will be known as a transpiler. And this transpiler will be used after compiling your source code, and then you get the transpiled circuits.
Can I ask you a simple question? Is it okay?
Yeah, please.
Yeah, it's quite interesting your work you've done. It's exceptional. My query is once you've done the assignment of mapping, how do you do the verification that your desired mapping is correct?
Yeah, desired mapping is correct means you can see this is the mapping which actually IBM itself providing. Okay, once you do that transpiler circuit, once you generate a transpiler circuit for a given problem, so I've given a simpler logical problem, one simple problem. So there is a simple 5-qubit problem, right? Now this 5-qubit problem, you create a transpiler. Once you able to execute the code, that is your transpiler will generate a transpiled circuit, and this transpiled circuit will be mapped into physical circuit. Okay, so our program is generating this transpiled circuit, and that's transplant circuit moving in a physical hardware. We have executed this entire process in our physical hardware in a IBM Q.
I meant, maybe I asked incorrectly. I meant once before you execute your program
Ah, yeah,
physically,
that is done by
or it's just the
yeah.
mapping, just to verify that mapping that you've done your optimization is
Yeah.
correct, is correctly
Ah,
set up before you
yeah,
run.
right. Yeah, that is totally classical PSO based algorithm, which we have before I creating the transpile circuit. So once it's the transpile circuit is generated, before transpile circuit generated, I get the optimization from the PSO algorithm. As I explained, the PSO algorithm giving you this, the F fitness value. If the fitness value is minimum, then that fitness values, that corresponding mapping we will consider as a best routing, right? So first I put this connectivity. Then if the verification is done that way, that if the SOP, POS giving my result is optimal or not. If that is compared to the different possible heuristic algorithms as well as all other evolutionary algorithms we have tested, and after that we come to closer that the SOP POS, particle sum optimization, will be the best way to optimize the result. And once the result is optimized, we get the transpiler circuit. The transpiler circuit will be also optimized. So that is the way of how we actually verified.
Yeah,
We verified with
yeah.
the different proposed model, what we have actually given in the comparative studies, a different proposed model that is most optimized way, and then we create a transpiler circuit, and transpiler obviously will be optimized one.
Yeah, thanks very much. It's clear now.
Sure. Thank you. Sir, many problem is there now. You might be go for that 1,000 qubits. If you even if you don't have this 1,000 qubits computer, but we can logically think of that the my problem is working over a 1,000 qubits computer. We are working with that also for this type of things. And even not only that, if you have a different devices, then which device will be the best one for your particular problem, that also be very important for your mapping or transpiler. The transpiler will also be selecting appropriate devices. That also we are doing. So more or lessly, the transpiler have a big role after compilations. Transpiler has a big role in a quantum as a meta wire, I must say. Otherwise, we cannot go for this. Because if I consider that the 1,000 qubits can be mapped to the 10 currently available quantum chip, then it's the 1,000 qubits. The only requirement is your transpiler, that is a meta wire. If a meta wire is ready, then you can connect the other quantum hardwares. So we are looking for that. And in India, we have opportunity to grab this opportunity. I need to grab this opportunity. I open-handedly I'm open for collaboration, open for collaborative work in this domain. And this domain is very important because metaware actually decide our future. Hmm. This transpiler will decide our future. Even IBM is planning for better transpiler.
I see a question from Bill Gonzalez. he asked, can we move to the slide before the references? The result.
This one? This one?
Bill, is it this one?
Previous? Or this one?
You mean the slide before the references? Before, I mean the second to the last page, I think. He wanted to see the result. Or maybe I can share the slides afterwards, if you don't mind.
Which one?
He said yes, yes. Bill Gonzalez said yes. And I also get an earlier question from George. Are there physical systems which can give qubit three-dimensional connectivities?
Physical system?
This would allow non-planar qubit graphs. Perhaps molecules can be treated.
Physical system?
Yeah.
Ma'am, if you can repeat the question.
So the question is on the chat from George Ziberland. Are there physical systems which can give qubit three-dimensional connectivities? This will allow non-planar qubit graphs. Perhaps modules can be treated. So let me pose a question again in the latest chat.
Can you give a 3-qubit, three-dimensional connectivity? This would allow the non. Yeah. That is a very interesting one. Yes. Let's see. Sorry. The 3 qubits, even not we are working with a 3 dimension, only 1D and 2D. If you have any idea, please contact me or you share your contact. I will definitely connect with you. It will be remains importance because 3-dimensional connectivity, if we able to make it, because one thing that the qubits are now in the 2D plane. If you go for a lattice structure, then definitely it will be in a 3-dimensional space. So perhaps it is a molecular. So definitely it's a molecular based qubits can be done, and that will be 3D model. And in a 3D model, the more connectivity will be there. Definitely, 3-dimensional connectivity. We can test it, but problem is that the hardware will not be available because hardware is only 2-dimensional hardware is available now right now. So please, I may request that I have shared my mail ID. I again writing here. If you have any idea or any collaborative work you are planning, please let me know. We can start together, or we make a big form of groups. In India, we are creating that type of groups. That is our national mission. National quantum mission is that we might be creating a cluster of universities, cluster of organizations, cluster of R&Ds, and startup companies. Those are using quantum as their research, so they can come together and make some ideas and develop new ideas. Yeah, obviously, I am interested with using non-IBM systems. It's okay, but only the IBM hardware is there. DUF don't require this type of transpiler because they have done only by cubo mapping by the Q matrix. But only the available is a IBM Q. IBM Q can be used as a commercial and or educational purpose. Definitely, if it is any other systems you have access, then we can work, because mapping what we have required to test, after transpiler circuit that need to be executed in a real hardware. Otherwise, the result cannot be justified.
And Bill
Any-
Gonzalez has a question. Are you interested in using non-IBM systems?
Other than IBM systems, more complex optimization problem would result a more level, that is Qubit. Yes, Qubit is required, but we are now concentrating on a Qubit only. Definitely, the Qubit are required as a level or your is increasing. So it's correct. It's your correct answer. Might be the Qubit would be the near future is a good solution. But still we are getting qubits, so hardware is available qubits. Now current problem is that to on using the qubits only.
So right now you're still using IBM systems, not something other than like IBM.
Yeah, I have answered it because IBM system is available for educational as well as your commercial purpose. In educational purpose in India, IBM have a collaboration with Indian government. They are giving educational purpose, it's a free of cost. So where in terms of other your gate level quantum computers what is available, namely a few were there which is available with our Amazon quantum bracket, which is more costly than the IBM Q. Frankly speaking, this if the and IBM Q have given an opportunity to produce their contribution to them for doing the transpiler design. Okay, so that somehow they are creating a open source mindset up. That's why we have worked. If we have any other access, definitely. Definitely, I am interested. We are interested because my working group, my PhD scholar is also there, also available here. Actually, who is working is this domain. I want to uh, uh, show you the Shubhasri Bhattacharya. Shubhasri Bhattacharya is just a thesis submitted student, PhD thesis submitted in a university. Uh, he's an he's our team and her team and our team works together. Actually, he's a assistant professor in one engineering college. Uh, he actually carried on his PhD work, and above than his PhD work on this field, he is interested in our qubit mapping, and we are open to work with other teams collaboratively. If we have a different devices, definitely for that devices we can create a transpiler and a more other logics. Because I saying that we are shaping that way how you can differentiate between the different hardwares that is possible, the optimal hardware for your particular problem that you can select by using the transpiler only. Any other question? I'll be happy to answer.
I noticed George Sibberland has a comment. At the nanoscale, we are able to put insulating layers between conducting and semiconducting layers to locally jump into the third dimension. It's just a comment.
It's a comment. Nano, I can say actually because we are a developer actually, software developing part. Your physical qubits, whatever you are designing, that is the different engineering, the quantum engineers, those are doing with chemists and definitely physicists and mathematicians are doing the quantum device design. But we are concentrating over that after the quantum device is ready, then how that will be interacting with our application programs. So that is a meta wire or transpiler that is required actually to making a bridge between application program and your hardware what you have developed. So that meta wire we are thinking of and we are working on it. But we can say what are the physical devices, how you are creating, that is your domain, not our domain actually. Anything else? Anyone want to know anything?
Yeah, please feel free to raise your hands and unmute and ask the questions.
One question comes. Oh, yeah. Thank you very much, sir. I'll be happy to work with you.
Okay, Terry Bolinjo has a question. What are your next steps? Do you see
Next
future
steps.
opportunities?
Yes, sir, is a good question. I want to Terry. Professor Terry is a very good question that I actually looking for. This is the idea about that first the building step of all getting the 10,000 qubits, even maybe 20,000 qubits quantum computers, even though you don't have 10,000 qubits chip, you might have only 100 qubits chip. And if I able to map the 100 qubits chip with 100 times, then how many times? How it becomes? It becomes 100,000, 10,000 qubits. So 10,000 qubits, logically your program can be, and metawire or transpiler will be able to map with a different 10 hardwares simultaneously. For that, what you required, you required that you have an internet. So that is going to the quantum internet. You have an internet or interconnectivity between the different chips. If you make a internet connectivity, that is that the concept is I'm coming from your parallel computer architecture. How the parallel computer architecture works? If you have a either interconnectivity network, so different devices, different processors are connected. Similarly, here the 100 processors are connected with the internet. So then the globally the 10,000 qubits mapping will be addressed by your transpiler, and transpiler you actually giving you the physical mapping which will go to the different devices. If you have 100 device, we have 100 qubit in each device, so it become a 10,000 qubit device. Our next planning is, sir, to develop this and open it into the our society to think that how we can go for 10,000 qubits very easily. It's a big work. It's a big work. It will require definitely 2 to 3 years research. Otherwise, we can't do this because it's a big challenges. Only over that 100, as you know, that is a NP complete problems. When n become huge, so your exponentially running time will increase. That's the challenge is that if you go for 10,000 qubits for 100 chips together, so then your problem is NP complete. So you move to the running time higher. Okay, so there are so many challenges will be coming, but we are thinking that first to let you know that which hardware is compatible for which your problem, which hardware will be best problem. Because you have now maybe in your future you have a 10 choices, 10 similar type of hardware you have, but you don't know which hardware is tuned when, calibrated when. So that calibration information, everything will be extracted, and transpiler will provide you that this hardware will be best automatically loaded to that, and corresponding mapping will be also best. If I make a mapping or transpiler circuit smaller, then automatically its complexity will be lesser.
That's an impressive opportunity. I like that's
Yeah. Definitely, it's a very, very good opportunity, and not only the very good opportunity, this is the most important part of quantum computing. You may have developed your several algorithms, but you don't know how to transpile and how to make it in appropriate hardware. It will be very tough. I can remember in 2017 when I started to code in a IBM. Then there was no transpiler. First, you need to check what is the physical mapping. According to physical mapping, you need to code your program. But now at least they have developed transpiler, and they are continuously improving on that work. We also working for the transpiler. Yes, there is so many questions because we have simply used 2 bits gates. That is the limitations. For the research purpose, it is the limitations that we have simply considered 2-bit gates and not all just a CNOT. But now we need to move to the rotational gates, and there are 3 bits rotational gates for U gates. So then only the actual commercial transpiler can be generated.
That's very forward looking. That's nice.
Yeah. We are actually looking for the fund, which actually providing the DST. Once the DST provide the funds for that part, definitely we will excel in this domain. And first we will create a indigenous 8-bit quantum computer, and gradually we'll increase the length, the size of qubits. Thank you. And I need a collaboration with all the entire world. Any other questions? Agree with it has excellent presentation. Thank you. Thank you very much. Any other, please?
So if there's no question, thank you for coming. Yeah, and I'll see you in 2 weeks. Yeah. Thank you.
Good presentation.
Thank you very much.